Let's revise the whole of forces in GCSE Physics. So we're going to start off with the difference between scalar quantities and vector quantities. So scalar quantities have a magnitude only. For instance, we can have the speed, the distance, or the temperature. It doesn't really make sense to talk about direction if we're discussing temperature, for instance. On the other hand, vector quantities have both a magnitude and a direction. Here are some examples. For instance, a force is a vector, velocity is the speed in a particular direction, and displacement is also a vector. We typically represent a vector with an arrow. And here are some examples of some arrows. We have a 2 Newton vector pointing upwards, and we also have a 4.5 Newton vector pointing upwards. The length of the arrow represents the magnitude, whereas the direction of the arrow represents the direction of the force. So for instance, if we're pushing something up, it will be pointing upwards. If we're pushing something down, it will be pointing downwards. You may come across a negative sign as well for the force if it's in the opposite direction. For instance, this one here is plus 2 newtons and this one here is minus 2 newtons. The force could also be at an angle, such as this vector right over here. So typically a force is simply a push or a pull. However, all forces could be classified as either contact forces, in which the objects are physically touching. For instance, there's a collision force between those two objects. Let's say that they're both moving towards each other. So let's say that this one here is going towards B and this one here is coming towards A. Non-contact forces are physically separated. An example of that could be gravitation, the electrostatic force, and the magnetic force. So what do I mean by that? So you can have, for instance, 2 planets or 2 stars orbiting each other, and they're actually exerting forces on one another at a distance. Examples of contact forces, on the other hand, include things like friction, air resistance, tension, the normal contact force, additionally any collision forces as well. A special type of force which we'll need to consider is the weight. Now this is the force due to gravity, and the formula for it is that weight is equal to mass times gravitational field strength. Symbolically, we would write this as W is equal to m times g. Now W here is simply the weight, which is measured in newtons. So let's just write the units across here, typically measured in newtons, and the mass is typically measured in kilograms, although we can get questions in which the mass is given in grams or another prefix, and we'll need to convert that. And g in this case is the gravitational field strength, which is just simply measured in newtons per kilogram. Because we're revising, let's also make m and g the subjects of this equation. So I'm going to take this equation and let's make sure we say the mass the subject of this equation. The mass will be then equal to the weight divided by the gravitational field strength. If we want to rearrange, on the other hand, for the gravitational field strength, then this will be equal to the weight divided by the mass. So the gravitational field strength on Earth is right around 10 newtons per kilogram. And if you're doing A-level physics, or if you're using a more accurate value, the real value is a lot closer to 9.81 newtons per kilogram. You would also see this measured as meters per second squared, which are actually equivalent units. So don't worry if you come across G being equal to, let's say, 9.81 meters per second squared. Okay, now moving on to the next revision point. The weight of an object may be considered to act at a single point, and this is typically referred to as the center of mass. And this is the definition that we would need to know if we're asked to define that in an exam. In the lab, particularly in extended response questions, we can measure the weight using a Newton meter, which is this spring-like device. Let's also do a small example. So we have a 10 kilogram object. What is the weight of this object? So the weight is just equal to mass times gravitational field strength, which is m times g. The mass is 10. We're going to assume that the gravitational field strength is also 10, which is going to give us 100 newtons. This next concept is extremely important. Let's talk a little bit about resultant forces. So we can have a whole bunch of different forces acting on an object, and the resultant force is used to replace the effect of all the original forces that are acting on this object. So for instance, if I have a 1 Newton force acting to the left and a 1.7 Newton force acting to the right, the resultant will be equivalent to a force of around 0.7 Newtons, which is acting to the right. If I have two equal and opposite forces, for instance, 3 newtons to the left, 3 newtons to the right, then the resultant force will be 0 newtons. Here are some examples. So for instance, the weight is always acting downwards. So if we have an object which is supported by a surface, the weight is acting straight down, but this object is not going towards the center of the earth because there is a normal reaction which is acting upwards. And this is an example of two forces which are fully perfectly balanced. Now this is a concept for the higher tier only. However, a single force can be resolved into two components which are acting at right angles to each other. So let's say they have some sort of a force which is acting this way. This could be any number. I'm just going to call it generally just F for force, and this will have a vertical component and a horizontal component, and those two components are at a right angle to one another. What does that mean? If I apply a force of this magnitude with a certain horizontal component, and then I apply a vertical force at the same time going upwards, the result will be equivalent to this force which is acting at some angle, which could be anything. So work done next, and a force does work on an object when the force causes a displacement. In other words, anytime we apply a force onto something and it moves, there's work done. Here's this person over here, and they're moving this big box across here with a force of 70 newtons. The work done is defined as the product of the force multiplied by the distance. Symbolically, we would write this as W for work done is equal to force times distance. Work done is actually just measured in joules, the force is measured in newtons, and the distance is measured in meters. So if we move this big box by a distance of 3 meters with a force of 70 newtons, the amount of work done that we're going to do will be equal to the force, which is 70, multiplied by the distance traveled, which is just 3 meters. So that's going to give us 210 joules. Interestingly, 1 joule is actually equal to 1 Newton meter because, well, you can kind of think of the force as being measured in newtons multiplied by the distance, which is measured in meters. Work done against the frictional forces actually causes a rise in the temperature of an object. So if you have loads of air resistance or friction, this will actually make the surface of the object increase its temperature. Kind of like a space shuttle, for instance, that it's going back to the Earth, all that resistance forces will cause its temperature to rise. Let's talk about forces and elasticity next. So forces can bend, stretch, or compress an object. But in order to change the shape of an object, we need more than one force. What do I mean by that? So let's say that we wanted to compress this object here on the right. So let's say I apply just a single force F onto it. Well, then if this is the only force that's applied to it, there's not going to be a compression, but what will happen is that this object will simply just move to the right. So what we want to do is apply another force to it, like so, and then if we were to apply both of those forces, then this object will compress. There's a difference between the types of deformation that can be caused. So for instance, we can have elastic deformation in which the object returns to its original shape, but we can also have inelastic deformation in which the object does not return to its original shape. So the relationship between the force and the extension is given by this law. It's actually known as Hooke's law, and the extension of an elastic object, such as a spring, is directly proportional to the force applied, provided that the limit of proportionality is not exceeded. So the force is equal to something which is known as the spring constant times the extension. Symbolically, we can write this as F is equal to K multiplied by E, where the force is F, the spring constant is K, and the extension is E. Let's think about the units. So the force will be measured in newtons as always. The extension is measured in meters, and to keep the units the same on both sides, the spring constant will be measured in newtons per meter. Let's do a little example. So what we have across here is just a little spring with a force of 20 newtons acting vertically downwards, and this spring is being stretched by an amount which is equal to 10 centimeters. So let's see if we can figure out what our spring constant K is. So this is our unknown. The first thing that we need to do is we need to take this equation and just rearrange it for K. So because F is equal to K times E, rearranging for K, making it the subject of this equation for our spring constant, this will be equal to the force divided by the extension. Now our force is equal to 20 newtons, our extension is equal to 10 centimeters. Let's convert that to meters, so this will be equal to 0.1 meters, and dividing those two quantities, we're going to figure out that K is equal to 200 newtons per meter. Yet another formula that we need to know is the formula for work done or elastic potential energy, and for to compress a spring or stretch it, we need to do some work. So for instance, if I had a spring like that, and if I wanted to compress it, I need to apply a force and move this object a particular distance. The formula for it is that elastic potential energy is given by a half times the spring constant multiplied by the extension squared. So the energy will just be equal to a half times the spring constant times E squared. And we also have a required practical for this topic, so we're going to investigate the relationship between the force and the extension of a spring. The way we're going to do this, we're going to set up a spring on a lap stand and we're going to hang mass off it. Our setup will essentially kind of look something like this. Let's do a perfect drawing around the side, and we are going to vary the mass and hence the amount of force which is stretching the spring. And because force is essentially the weight, which is equal to mg, we could also write this as W is equal to mg. We're going to be measuring the extension E. The way we're going to do that is we're going to set up another ruler directly behind it, and we're going to be taking some measurements. We're going to measure the mass with a top unbalance and the extension with that ruler. We're going to be quite careful to take measurements at eye level to avoid a parallax error. After that, we're going to plot a graph with the force on the y-axis and the extension on the x-axis. The graph should be a straight line for the origin if the force is proportional to the extension. In reality, if we go above the elastic limit, so I just draw this in a different color. we're going to get a line or a graph which is no longer a straight line. In fact, it will start to curve, and this point here is actually known as the elastic limit. And whenever this relationship is no longer a straight line, then we're not having a force which is directly proportional to the extension. So here we can say that force is proportional to extension. So let's just write this down. It's proportional to E, whereas here the force is not proportional to the extension. We can get especially some multiple choice questions occasionally with various different shapes, but as long as the graph is no longer a straight line, the two are no longer proportional. Let's talk about moments next. So a force or a system of forces may cause an object to rotate, and this turning effect is known as the moment of a force. The formula for it is that a moment is equal to force multiplied by distance, and symbolically we would write this as m, the moment, is equal to the force times the distance. The unit for a moment is Newton meters, whereas the unit for a force is just newtons, and the unit for the distance is meters. Typically, the situations that we encounter in moments involve these levers in problems. Here's an example of a balanced lever. We have a 5 Newton force which is acting 2 meters away from the pivot. So the 2 meters is the distance from the force to the pivot, so up to here. And then we have another 5 Newton force acting at the same distance. So both of these forces are exerting equal and opposite moments, hence the object is balanced. We can also actually separate them into clockwise and anti-clockwise moments. So this one here is going down. So if it was the only moment that's acting, this object will rotate in the following direction, which is anti-clockwise. Whereas if we had just this moment acting, then the lever would rotate in this direction, which is clockwise. So should we just write this down? Clockwise and anti-clockwise. Okay, well, we can use this to do a whole bunch of different interesting calculations. So we have a 2 Newton force which is acting 2 meters away from the pivot. However, now we have a force F that is acting much closer, 0.75 meters away from the pivot. So how can we determine the amount of force? All we need to do is equate the two moments. So our initial moment is going to be force times distance. Often I'll just write F1 D1 is equal to F2 multiplied by D2. Now my first force is just 2 newtons multiplied by 2 meters, and this will equal to my second force. Let's label that as F2 multiplied by the second distance, which is 0.75. So 4 will be equal to F2 times 0.75, meaning that F2 will be equal to 4 divided by 0.75, which is around 5.33 newtons. We can also use gears to transmit the rotational effect of forces. So gears are typically found in things like bikes and cars and other machinery. But if a gear is made larger, it will rotate more slowly, but it will have a greater moment. Notice how the two gears are rotating in opposite directions. So if this gear is moving upwards, it will push the following one up. So in a way, the smaller gear is moving clockwise, whereas the larger gear is rotating anti-clockwise. Now, the forces acting on the gears are identical, but their moments are different. And this is the crucial difference that sometimes pops up in questions. So, in a way, turning a gear that has double the radius doubles the moment, i.e. doubles the turning effect. If we were to increase the radius by, let's say, a factor of 4, then the moment will increase by a factor of 4. And now let's talk about pressure. So typically with pressure we're dealing with a fluid which can be either a liquid or a gas. And a pressure is defined as the force normal to a surface divided by the area of that individual surface. Mathematically, the pressure is just force over area, where the pressure, or the unit for pressure, is the Pascal, the unit for the force is once again the Newton, and the unit for the area is meters squared. So a Pascal is actually equivalent to newtons divided by meters squared. Now if you're doing the higher tier physics, then you also need to be aware of this equation, that pressure is equal to rho hg. This symbol here, this curly p, is just this symbol rho, and this simply means the density of that fluid. And this here is an equation for the pressure at the bottom of a column of a fluid. So if I had a diver across here, what sort of pressure would this diver be experiencing? Well, the formula is giving us that pressure. So let me just annotate this. This here is the pressure, this weird curly p symbol called rho, that's just the density. H is the height, and G is gravitational field strength or gravitational acceleration. Okay, so we can use that to calculate the pressure of a diver at a given height below a column of water. Let's apply this equation to a sample problem. If the density of water is 1000 kilograms per meter cube, calculate the pressure due to the water of a diver that is 5 meters below the surface. So imagining that this column of water is 5 meters, how many pascals of pressure would this diver actually experience? Well, the pressure is equal to the density times the height multiplied by g. Therefore, this will be equal to 1000, which is our density, multiplied by 5 multiplied by g, which we're assuming that it's 10. And this will give us 50,000 pascals. Now this immense pressure is due to molecules, the weight of the molecules that is directly above the diver. So if there's more water above the diver, if they're lower, and then the pressure will increase. And this leads us to the concept of atmospheric pressure. Now, the atmosphere is just a thin layer relative to the size of the Earth of air around the planet, and the atmosphere gets less dense with increasing altitude. Essentially, air molecules are colliding with the surface, and this is what actually creates atmospheric pressure. So if we were to go up on a plane, or if we were to climb Mount Everest, there's going to be less molecules colliding with us, decreasing the pressure. Additionally, the weight of the air above us is really important. So the number of air molecules and the weight of the air above a surface decreases as the height of the surface increases. So as the height goes up, there's always less air above the surface, so the atmospheric pressure decreases with height. On to Newton's laws. Newton's first law: if the resultant force on an object is 0, well, first of all, if the object is stationary, it will remain stationary. However, if the object is moving, it will continue to move at a constant velocity. For instance, we can have a car that is moving at a constant speed, so we can say that it's moving at a constant speed, and that would indicate that the driving force F will have to be equal to the resistive forces in terms of magnitude, but opposite in direction. Newton's first law is related to the tendency of objects to continue in their state of rest or uniform motion, and this is called inertia. So objects continue to remain at rest or move in a uniform motion unless there is an external force acting on them. Okay, Newton's second law, the acceleration of an object is proportional to the resultant force that is acting on the object. And it's also inversely proportional to the mass of the object. Mathematically, we can write this as force is equal to mass times acceleration. This is probably the most famous equation from Newton, that F is equal to ma, where F is the net force. Please pay attention that this here is the sum of all forces rather than individual force. The mass m is just measured in kilograms. The force, as always, is just measured in newtons, and the acceleration is measured in meters per second. Rearranging for the acceleration, we get that a is equal to F over m, force over mass. And additionally, the mass will also be equal to the force divided by the acceleration. Now, there is a required practical to investigate this relationship here. The way we're going to do this required practical, which can come up in an extended response question, is to use an air track, and then we have a little card, a little interrupt card, and some light gates. The air track is connected to a little vacuum that pushes air out, and that removes friction from the system. The cart is connected via a string to a bunch of weights over a pulley. So this thing here is just a pulley, this circular object just here. So what's actually happening is that the weights are actually applying a force and pushing the cart through the light gates. So we're going to vary the force by adding in more weights, and we're going to be measuring the acceleration for a constant mass. We're going to measure the acceleration with the light gates. Those will typically be connected to a data logger that will give us the acceleration directly. Then we're going to plot a graph of the acceleration on the y-axis against the force on the x-axis. So that's one option. You may do it slightly differently, or but if the acceleration in meters per second squared is on the y-axis against the force in newtons on the x-axis, we should get a nice straight line relationship. Okay, on to Newton's third law. When two objects interact, they exert equal and opposite forces on each other. So if we have object A, let's say that is on a collision course with object B, so what's going to happen is they're going to smash like this, and then they're going to exert equal and opposite forces. What do I mean by that? So object A will experience a force due to object B, which is going this way, and object B will experience exactly the same amount of force but going the opposite way. Okay, so let's also revise stopping distances. So in a nutshell, a stopping distance is the sum of the thinking distance plus the braking distance. So the thinking distance is simply the amount of distance that the car will be traveling before you press the brake pedal. So you see a hazard and your reaction time is a certain amount, and the car travels some distance. This is your thinking distance. The braking distance is the distance from pressing the brake pedal to the car coming to a complete stop. Now, your reaction time can vary from a person, but if you're asked to estimate it, a value between 0.1 and 0.9 will typically be fine. Factors that can affect your reaction time are tiredness, distractions, drugs, and alcohol. The braking distance of a vehicle, on the other hand, can be affected by adverse road and weather conditions or just poor conditions of the vehicle. So things can include wet or icy conditions, or poor condition of the vehicle will be limited to the brakes or tires. Something really interesting, but when a force is applied to the brakes of the vehicle, there's work done by a frictional force between the brakes and the wheel, and that reduces the kinetic energy of the vehicle. So the temperature of the brake increases, and sometimes you see in racing cars that the braking discs actually start glowing because of that energy that's being dissipated. The greater the speed of the vehicle, the greater the braking force needed, and the greater the braking force, the greater the deceleration of the vehicle. Okay, and our final revision topic is momentum. Momentum is defined as mass times velocity. The mass is measured in kilograms and velocity is of course measured in meters per second. So therefore the unit of momentum is just kilograms meters per second. Momentum is typically given the symbol P, don't confuse that with pressure. M, of course, is the mass, and the velocity is just V. Momentum, by the way, is a vector quantity because it's dealing with velocity. We need to be able to recall the law of conservation of momentum, and that is that in a closed system, the total momentum before an event is equal to the total momentum after the event. This is best illustrated with a little problem. So imagine that we have this 10 kilogram mass that is moving this way and a little 5 kilogram mass that is initially stationary. So after the collision, those two objects actually stick together and start moving together at a certain speed. And that's what we need to figure out. Okay, well, let's first of all calculate the total momentum before the collision. So I'm going to say that P before is equal to mass times velocity of this object plus the momentum of this object, which is just 0. So this will just be equal to the mass, which is 10 kilograms, multiplied by the speed, which is 10 meters per second. So the total momentum before will just be equal to 100 kilograms meters per second. Okay, well, the total momentum before will be equal to the total momentum after, and we can use that to calculate the total speed after the collisions if those two objects have collided. So the total momentum before was 100, and that's equal to the momentum after, which is equal to the total mass after multiplied by the speed after the collision. I should have just called these M2 and V2. Okay, well, 100 will be equal to, what's our total mass after now that they've collided together and they're moving as one object? That will just be 15 because they're stuck together, multiplied by V after, and we can work out that V after will be just equal to 100 divided by 15, or that will be around 6.7 meters per second. And this is kind of a tricky example with momentum, but really illustrates the idea. Okay, there's just one more equation that we need to know about, and we can combine the F is equal to ma equation, Newton's second law, with our definition of acceleration, which is v minus u, final minus initial velocity, divided by t. Now what I'm going to do is I'm going to take this equation, I'm going to plug this into here, and what we're going to get is that force is equal to mass, and rather than acceleration, I'm going to write v minus u divided by t. Okay, well, let's expand this, and what we're going to get is mv minus mu divided by t. But if we think about it, mass times final speed, take away mass times initial speed, this is just equal to final momentum take away the initial momentum divided by time. And another way of writing this is that this is equal to the change of momentum divided by time. So the net force is actually equal to the rate of change of momentum. Okay guys, well done on revising an entire topic in this really long video. Now, I've not included motion, and you absolutely need to revise this if you have an upcoming mock or you're revising for the real exam, and this video is right over here, so click over there.